So again, this is a short topic, and it's not critical that you understand it. Vector algebra is, however, something that helps us to understand regression models, and it's somewhat useful to think about our variables in terms of their standard deviations rather than the variances. And it has some relationship to the issue in this class of rotation when we get to exploratory factor analysis. So it stands a little bit by itself. When last we stopped on Friday, I was at this point, and the thing that I had been wanting to say was in vector algebra, two variables that are indicated by vectors, that is, have a point on one end and an arrow, where the length is the standard deviation, two variables are assessed in terms of their similarity by the angle between those two. So what I do is, if I have one vector, these are both pointing in the same direction, I slide the endpoint of one vector over to another, and then I look at the angle between the origins of those two vectors. So if I did that to this variable, I'd slide it down and observe, oh, the angle here is 0. That is, that's a way in vector algebra of saying that these two variables are perfectly correlated. Well, it's been quite a few years for most of us since you took trigonometry and even thought about cosines. So I thought it's probably helpful to look a little bit at angles and what a cosine is. And way back when you do geometry, it's helpful to have a little mnemonic. I just love collecting them. And one of the things that we often talk about in trigonometry are what are called the principal angles, the 0, the 30, the 45, the 60, and the 90-degree angle. And one way to write out sines and cosines rather than memorizing them all in your head is to fill out a little table for yourself according to this pattern. You'll write the names of the angles on the top, and then write 0, 1, 2, 3, 4, and then write square root, square root, square root, square root, and then divide by 2, divide by 2, divide by 2. And to do the same thing for the cosines, except in reverse order. 4, 3, 2, 1, 0, square root all of them, and divide by 2. And you can solve those. That will then give you the principal angles that are involved for the sine and the cosine. And that's just kind of a fun thing to remember. And the moral of our story is if the angle between two vectors is 0, the cosine is 1, indicating a correlation of 1. And if the angle is 90 degrees, it's 0. So it's helpful to think a little bit about what a correlation coefficient is and what angle is represented. And this is a little table. So if I have a 0-degree angle between two of them, a 0 correlation, that's a 90-degree angle. And all the way over here, like 0.7, that's a 48-degree angle. And a 0.9 correlation is a 26-degree angle. Similarly, if we think about this in terms of R-squares, proportions of variance accounted for, these are what the angles look like. So if I'm explaining 1% of the variance, the angle between my two vectors is 84 degrees. If I'm explaining half the variance, that's about a 45-degree angle. And if I'm explaining 90% of the variance, that's an 18-degree angle. So visually, this is what it looks like between two vectors. So here's my 0 correlation, and here's a 95.95 correlation, and so forth. And here's the same degree of relationships between vectors for an R-square model. And as I mentioned before, if two variables are negatively correlated, they're simply pointing in opposite directions. So if two variables are correlated -1, you'll see an arrow pointing here, and going over here to the left will be the other vector. That makes sense so far? Okay, so That gives us the strength of the association. Now we've got these vectors, their length is a standard deviation and there's an angle. What can I do with them that's interesting? I can add vectors together. So let's assume that our data are in deviation score form. And I have one variable A and another variable B. And I want to answer the question, what is the standard deviation of the sum of those two variables going to be? So here's what it looks like in a picture form. Here's variable B, and here's variable A, and here's the angle between them. If I want to figure out what the standard deviation is of the sum of these two variables, I'm going to take my variable A and slide it over until it touches the end of that vector, as shown in this picture. And the length of this vector that starts where B started is the standard deviation of the sum of those two variables. It's a little bit more fun if I'm doing it in class with, overheads. I can have a vector and slide them over and you'll see the action. Just for practice, if I've got A and B positively correlated, I'll have this length. If A and B are negatively correlated, here's A and B. And just do the same thing. I'm going to slide A over to the endpoint here. And the length of this variable is the standard deviation up to negatively correlated variables. And similarly, the length of the sum of two orthogonal variables is this. Is that working? So we can make just a few observations from the geometry that if my two variables are negatively correlated, the standard deviation of the sum is going to be smaller than if my two variables are positively correlated. Is that working? And if they're orthogonal, it's going to be some intermediate value. And I go through a little bit of, if you were really paying attention during geometry, there's a little bit about the half angle formula that relates to. All right. Yes, sir.
Can you scroll up to the picture again?
Yes.
So for after you slide the vector A to start in A plus B, where's which angle that we use?
Oh, okay. The angle that I'm using in the start is the angle when the 2 points of the two vectors are joined.
After you add it?
Right. In other words, the way this story goes is, once upon a time there were two variables. A had a standard deviation of this, and B had a standard deviation of this. And the correlation, the cosine of this angle, was how associated those two variables were with each other. And to do the operation of addition, I slide the point of one variable to the end point of the other. And going from the point to the end point of the second variable, the length of this line is the standard deviation of the sum. And so for examples, this is an example of two variables that are positively correlated because this angle is less than 90 degrees. this is an example of two variables that are negatively correlated because the angle is greater than 90 degrees. But if I do the same thing, I take this variable and I slide that point on A over to the endpoint of B, the length of this line is the standard deviation that would result if two variables were negatively correlated. Is that working, Andres?
Yes, thank you.
Okay. Well, so let's do something fun. Let's now look at what regression looks like. So here's the picture. One regression using variable vectors. And the reason that this is interesting is it's going to explain to you why statisticians always seem to be talking backwards. They talk about the regression of y on x. So I draw your attention to, let me make this a little bigger for those of you on devices. So here we have two variables, x and y, and the length of this line is the standard deviation of x, and the length of this line is the standard deviation of y. And the correlation between the two is the cosine of this angle. What this is, remember that I can multiply any vector by a constant. And in the case of regression, if I multiply x by the unstandardized regression weight, I'm going to have a new vector that will have a length that's this. Now, looking at this, I have a vector here, and a vector here, and a vector here. The angle between this vector and this vector is 90 degrees. It's shown by that little box. So what we're doing here is we're explaining how a regression works. That there exists a number, the unstandardized regression weight, which will adjust my predictor variable to have a new length such that the sum of y predict plus y residual is going to give me the standard deviation of y. Or if you think a little bit about our old friend Pythagoras, the square of this plus the square of this is equal to the square of this. Well, the square of y is the variance of y. The square of y predict is the variance of y due to x. And the square of the residual scores is the error variance. This explains to us graphically why it's a good idea to have a right angle here. Because if I chose any other number for the regression weight, say one that was way over here, I don't know if you can see my pointer, but I'm in the middle here. The length of this line of the error variance is going to be larger than it would be than if they were orthogonal. So that takes a little digesting, but is what I'm saying making sense?
I have a question. Here, does B stand for slope?
Yes. The
Okay.
unstandardized regression rate is a number that I can multiply the x variable by to create a new vector that has, in this case, a smaller length than the original variable.
Thank you. So is it always be orthogonal like that? So do we take projections?
Yes. And so if we had another scenario, let me see, I don't know if there's any way for me to get different size pointers. I should. No, it won't let me do that right away. So I'll have to practice up on my Zoom skills. But if I had any other number than the unstandardized regression weight, that's going to result in a vector going up to y that's going to be larger than the vector that I have from the orthogonal multiply, the number that I get to fall directly underneath the y variable. And so, I mean, the fun thing about this for people who are geometry minded is that, you know, it always comes down to the Pythagorean theorem that this squared plus this squared gives me this squared. And since we're playing, the length of all these lines represent standard deviations, it's a little bit easier to think about. Now, just to think about what another equation looks like, this equation is what this diagram is. If I flip that and I start looking at x as the criterion and y as the predictor, this is what my diagram will look like. That it will be, here's the length of y, and I'm going to have some coefficient that changes the scale of y so that it falls directly underneath x. That's why the unstandardized regression weight predicting x from y is different than the unstandardized regression weight predicting y from x. And that's me trying to think of, you know, something interesting to say about the basic one predictor model. And that's in equation form, what I'm saying down here, that the variance of y is the variance of y predict plus error variance. And the variance of y predict is b squared times the variance of x plus error. We can extend that situation to the case of two predictors. Let me make it a little bit larger. So now we have x1 and x2, and y is this variable that sticks out. So x1 is this variable, x2 is this space, x1 and x2, and y is the thing that stands up outside, you know, up from this little plane. Well, the unstandardized regression weight for the first variable and the unstandardized regression weight for the second variable is the sum of b1 times x1 plus b1 times x2 that gets us to fall right beneath y. And the length of this vector here is the error variance, that it is the variability in y not explained for by x. And the length of this line on the x1, x2 plane is the standard deviation of y predict again.
I have a question.
God bless you, yes.
Can we make the pictures larger again?
Yeah, you want this one?
Yes, I want this one. So here, what I see from the picture is B2, X2 is on the same surface with X2.
Mhm.
However, I guess we make a projection, or we did something to bring X1 to the X2 surface, I guess, because it is pointing upwards.
Yes.
So y, so the opposite, and can we just turn it, and then x1 can be as can x1 be a surface, and then we project x2 b2? This is first question. The second question, why did we do this? Like to get this projection.
Okay, well, if I understand what you're saying, yes, I could rotate this surface and have it sit flat on the ground and do the same math. And what we're doing here is is to show the relationship between x1 and x2 and y. So the angle between x1 and x2, if I just look at this pointed arrow and this pointed arrow, that's the correlation between x1 and x2. And the angle between x2 and y, that would be the angle here, is the correlation between x2 and y. And similarly, the angle between y and x1 is the angle from the leftmost vector and the right one. But our adjustment for figuring out what the standard deviation of y predict is the sum of some number that I multiply x2 by to get a new version of x2, and some number that I multiply x1 by to get a new version of x1, such that when I add this plus this, I've got a new vector here, and the endpoint of this vector falls directly underneath the y. And that's, all that, that's all that I intended to show in the picture, that this corresponds to the equation y is equal to b1 times x1 plus b2 times x2. And geometrically, what that's showing is I'm getting a new vector by adding those two vectors together that gets me a vector that falls directly underneath y.
Okay, I think I understand.
Okay.
Is just projection of the real vector times b1 x1. Is that correct?
Yeah.
If okay, I think I can understand it. Thank you.
Okay. Now, for some people, I mean, the rest of this is me spelling out what I've learned in other classes I've had before, but it relates to the general idea that we can think about our data in one of three score matrices. If all of the lengths of the vectors I talk about have length 1, I'm dealing with a situation where I'm looking at standardized regression weights. So, for example, here, let me make it larger. If the length of this line is 1 and the length of this line is 1, the regression weight that I multiply x by to fall directly underneath the standardized version of y is the standardized regression weight. And similarly, in the case of a two-predictor regression model, if the length of y is 1 and x1 and x2 is 1, these coefficients down here are also going to be the standardized regression weights. Well, the third thing you can do is you can think about your data in the adjoined matrix form. So I would be doing a regression with a column of 1s. And this is what it looks like. I'm going to have a column of 1s here, and I'm going to think about the average sum of squares of x. So this big X means I'm taking the raw scores in my data, squaring them, adding them up over all the rows, and dividing by the sample size. And the mean represents the number that falls underneath the sum of squares. And the length of this line will now represent the standard deviation. So let me say that again. I start with a column of ones and another average sums of squares product. The number that falls directly underneath the endpoint of this vector is going to be the mean, and the length of this line will now be the standard deviation of x. Well, using Pythagoras, this is now saying the same thing as we talked about before. The variance plus the mean squared is equal to the average sums of squares. And for the case of a one predictor regression model, I would have an x variable and a y variable and the column of ones, and I would again have a three-dimensional picture where the length of these lines would be x and y, and I would be explaining these sums of squares of y. And again, you will never use this fact in the rest of this class, but I'm showing it to you saying, well, the geometry does exist out there for us to do this, and it's the same geometry regardless of whether you are dealing with the deviation or the adjoined matrix. I talk a little bit about a t-test for two observations, and in the interests of time in the semester, this is not something that you would need to have for structural equation modeling, but it does talk about how you can use vector algebra to figure out if something is statistically significant. So I don't hold you responsible for it, but if you're interested in reading it through, it's there for you, and you can, say, oh, gee, there's a geometry that underlies the t-test and a geometry that underlies the F statistic, but I'm going to skip that, if that's all right. So why do you care about vector algebra in this class? Well, in factor analysis, we talk about our variables as being vectors. And for reasons that will come to the fore when we talk about exploratory factor analysis does a couple of things. First of all, it comes up with an estimate of what the standard deviation of a variable is in absence of any measurement error. And secondly, it represents how those variables are related to each other by means of vectors. And what you will find then is, if say you did an exploratory factor analysis and you had two factors, is you'll have these plots. And a factor loading for a given variable will be the numbers that correspond to the endpoints of the vectors for that variable. And the degree to which one variable is correlated to another is the cosine of the angle between those variables. For math reasons that I won't get into, it's the first vector representation that factor analysis gives you is frequently going to look like this, with you having a whole bunch of loadings on one factor that are positive, and half of the loadings roughly on the second factor that are positive, and half of them that are negative. And the act of rotating these around is spinning these vectors around so that there's a very small variance on one factor and a very large variance on the other factor that explains each of these corrected for measurement error versions of the data. And Varimax rotation assumes that there is zero correlation between factor 1 and factor 2. There exist models where factor 1 and factor 2 have a correlation. And when we allow for that correlation, we can express our two factors as having strong loadings on one factor and very, very small loadings on the second factor. And we don't need to go too deep into that, because when the time comes, I'm going to say, remember, we drew vectors that were the standard deviations of variables way back when. And we'll talk about rotation in that form. So that's a good place, to stop the discussion of vector algebra. I hope that that's, somewhat okay. And if you're curious about statistical significance testing and vectors, we've got the material there. But like I said, that's just me drawing things together in my own head and putting it all in one place. What I would like to do is to come back to the question of influence diagnostics. And when I did a little poll the last time on Friday, we talked about the preferred software platforms that people have. And most of the folks said they did R, and a couple of people said they did SPSS. So in the interest of serving the most people the quickest, I'll start out with R. So what I had said at the beginning of the class was that one of the reasons that Onyx is nice is that it gets you very quickly onto your preferred software platform. And one of the videos that I had given shows how to get Onyx and load it and play with some data sets. And just to rehearse that, what I had wanted to do was to have you, when the time comes and I send out a homework, be able to read a data set in, specify a structural model, and then run that on lavaan so that we can look at the influence diagnostics. So let's start at the beginning. Assuming that I fired up Onyx, I'm going to come in and load model or data. And the data set that I had attached to today's message is the McCardle data set. And lo and behold, there they are. And to do a structural model, I will create an empty model. I will select the first variable, hold down the shift key, select the next one, and drag that over here. In order, what I'm going to do here is to specify what's known as a latent basis growth curve model. And when we get into growth, we'll talk about that. But for now, all you care about is it's a picture. So to produce my factor analysis, my confirmatory factor model for the growth curve, I'm going to create a variable that's going to be a latent variable. And this follows pretty much the video that I've done on the YouTube channel. So I'm going to give this a name. I'm going to call this intercept. And I'm going to fix the path on that to the number 1. Wait a minute, I'm not. I'm going to free that parameter, I'm sorry. Getting ahead of myself. And now I'm going to make another latent variable. I'm going to call that growth or slope. And on this one, I'm going to fix that parameter to 1. I can move that down a little bit to make things a little tidier. Now I'm going to draw arrows from this intercept variable to the number 1 by right-clicking and dragging across. The paths, the loadings of this variable, are all going to be fixed at the number 1, and the variance is free. Now I'm going to draw arrows from my latent variable to each of the variables in turn here. I'm going to free these. And to make the the diagram a little tidier, since these names get really large, I'm going to start giving them names like L1 for loading number 1. And similarly for the next variable, L2. And feel free to ask me questions as I'm doing this. L3 and L4. So just to rehearse, this is a story. It says, once upon a time, I have 4 variables. These are whisk scores at 4 times of measurement. And that's a function of 2 latent variables, a latent variable that has factor loadings of 1, and a latent variable that has freely estimated loadings. I don't have a triangle in my picture so far, so I'm in the deviation score matrix. I do point out, and we'll talk about it later when we formally get into it, that this model has a name. It's called random intercept factor analysis. But I want to do a growth curve model. So in order to do that, I'm going to need to be in the adjoint matrix. I'm going to need my column of 1s. And I'm going to freely estimate the mean of the first factor and freely estimate the mean of the second factor. Now, I've played with this data quite a bit. I also know that I can make an assumption about these data by snooping at it, that I can actually set the error variances for the first 2 measurement occasions to be equal to each other. And that's accomplished by giving them the same name. This is a growth curve model. Now, very frequently, I often send the data to the model just to be sure that this data set is getting sent to that particular model. I can give this model a name. Like latent basis. And you'll see up here, there's a little triangle up here that says, I don't really like this model, but that particular aspect of Onyx is not incredibly reliable. What I'm doing, though, in this is I want to use the Onyx diagram to generate for me lavaan code. So I come down here and I say show script, and I arrow down here to lavaan. And this is the resulting Levon script. And this is the program that I will use to run my confirmatory factor model inside of R so that I can then come in and look at the influence diagnostics. The only thing I need to do is to possibly change the working directory Levon looks at so that it's running in the place I want it to, and to tell Levon where the name of the data set that's here. A little bit of orientation. As I mentioned before, Levon uses a line-by-line equation form. So this first command says, hey, I want to use Levon. The second one reads the data in so that Levon can process it. If the names of the variables are on the first row, I say header equals true. And what follows down here from the model statement down to the bottom is the equation form of the diagram I just drew. Intercept is the latent variable. I'm sorry. I named it intercept. That's this circle. And I'm going from this one to whisk one. So that's this arrow. and intercept to WISC2 is this arrow. I apologize. Haven't fully had my coffee. And the next thing are the arrows that are involving the loadings. So slope is this latent variable, and that goes down to L1, a free parameter, and same song, second verse for L2, L3, L4. The residuals are denoted by two tilde signs. So this is the E1, it's the name of the variable, that's the error variance associated with WISC number 1. That's this thing down here. And the same thing also happens for WISC 2, 3, and 4. So the intercept has a freely estimated variance. Intercept tilde tilde intercept tells me I'm looking at the variance of the intercept variable. And var intercept star tells me that's a free parameter. Slope tilde tilde slope tells me that's the variance of slope. And the star here says that the 1.0 here tells me that that is a fixed value. And intercept tilde tilde slope 0 tells me that there is a 0 covariance between the intercept and the slope. Now we're down here at the means, and the means are denoted by the number 1. So intercept tilde 1 tells me that I'm estimating a free value for the mean of the intercept variable. Slope tilde 1 is the mean of the slope factor. And these 0 tildes tell me that the error variances for WISC 1 through WISC 4, I'm sorry, the variables WISC 1 through WISC 4 have 0 intercepts. Right? Is that working? And the last line is executing the Levon code, and summary is going to show me the results.